Okay, so kinetic energy. You guys have probably heard about kinetic energy, probably about grade 7 or so, something like that, I'm not sure. Push on an object, you can set it in motion. If an object moves, then by virtue of that motion, it's capable of doing work. It has energy of motion, or kinetic energy, Ke. The kinetic energy of an object depends upon the mass of the object as well as its speed. It's equal to 1/2 the mass multiplied by the square of the speed, or Ke is equal to 1/2 mv squared. I will derive that for you in a few minutes. Yes, because you were probably wondering. When you throw a ball, you do work on it to give it the speed it has when it leaves your hand. The moving ball can then hit something and push against it, doing work on what it hits. The kinetic energy of a moving object is equal to the work required to bring it to that speed from rest, or the work the object can do in being brought to rest. So if you apply 100 joules of work to the object, it will have 100 joules of kinetic energy when you're done applying that work. The energy must be transferred. In shorthand notation, work done, Fd, is equal to 1/2 mv squared. It's important to notice that the speed is squared, so if the speed of an object is doubled, its kinetic energy is quadrupled. This means that it takes 4 times as much work to double the speed of an object, and also that an object moving twice as fast as another takes 4 times as much work to stop. And oddly enough, this ties in with what we were doing yesterday. Accident investigators are well aware that an automobile traveling at 100 kilometers an hour has 4 times as much kinetic energy as it would have traveling at 50. This means that a car traveling at 100 will skid 4 times as far when its brakes are locked as if it would traveling 50. This is because speed is squared for kinetic energy. Kinetic energy underlies other seemingly different forms of energy, such as heat, sound, and light. So, for example, yesterday, we all agreed that he was traveling approximately 70 kilometers an hour, and it took about 28 meters to stop, right? So if he was traveling 140 on the highway, well, then it would take him 28 times 4. What's that? 112 meters to stop. And that's the actual braking distance. That doesn't include the distance that you travel in the time it takes for your foot to go from gas to brake, right?
Some of those people in those accidents were going really fast.
Yeah. What did you think about the video where the guy was driving and he didn't have a seatbelt on, he hit and he sort of ended up like in the back of his car, all sort of... It was pretty surprising, I found, how much you get, literally like he said, like the Yahtzee dice, right, in the cup, tossed around in there, yeah. What about that person that hit that parked car with his face? Yeah, wear a seatbelt, please. Yeah. Okay. Flip the page over. Conservation of energy. Flip the page over. Okay, Ryan, put it away. Listen. Conservation of energy. More importantly than being able to state what energy is, understanding how it behaves or how it transforms. You can understand nearly every process or change that occurs in nature better if you analyze in terms of a transformation of energy from one form to another. As you draw back the stone in the slingshot, you do work in stretching the rubber band. The rubber band then has potential energy. When released, the stone has kinetic energy equal to this potential energy. It delivers this energy to its target, perhaps a wooden fence post. The slight distance the post is moved multiplied by the average force of impact doesn't quite match the kinetic energy of the stone. The energy score doesn't quite balance. If you investigate further, you'll find that both the stone and the fence post are a bit warmer. By how much? By the energy difference. Energy changes from one form to another. It transforms without net loss or net gain. If you've ever played racquetball, you'll notice after a while of playing, the racquetball itself is warm. How come? You're transferring energy to it all the time, and it's constantly being stretched and compacted, and there's friction, and some of that energy is given off as heat.
That's why you warm it up.
Yeah, because it actually bounces better, right? Is that right? Yeah? Racquetball or squash set? Squash, yeah. I've been out to the squash courts for a long time. The study of the various forms of energy and the transformations from one form into another has led to one of the greatest generalizations in physics, known as the law of conservation of energy, which says energy cannot be created or destroyed. It may be transformed from one form to another, but the total amount of energy never changes. When you consider any system in its entirety, whether it be as simple as a swinging pendulum or as complex as an exploding galaxy, there is one quantity that does not change: energy. It may change form, or it may simply be transferred from one place to another, but the total energy score remains the same. And there's the picture right there, right? You've got potential energy there. Here you've got potential energy plus kinetic energy. At the bottom of the swing, you've got only kinetic energy. And then, of course, it goes back up and you gain potential energy. Okay? It's very much related to conservation of momentum, and we're going to have to cover momentum in a bit. So that was pretty awesome. Now that we're back recording, I was so glad that we could go outside and show you that fantastic thing.
Yes. It was a lot.
That was pretty awesome, eh?
Yeah.
That might be the best thing I've ever seen.
Bad for Steve K, not me.
Flip the page. This energy score takes into account the fact that the atoms that make up matter are themselves concentrated bundles of energy. When the nuclei or cores of atoms rearrange themselves, enormous amounts of energy can be released. The sun shines because some of this energy is transformed into radiant energy. In nuclear reactors, much of this energy is transformed into heat. Powerful gravitational forces in the deep, hot interior of the sun crush the cores of hydrogen atoms together to form helium atoms. This welding together of atomic cores is called thermonuclear fusion, not cold fusion. This process releases radiant energy, some of which reaches the Earth. Part of this energy falls on plants, and part of this later becomes coal. Another part supports life in the food chain that begins with plants, and part of this energy later becomes oil. Part of the energy from the sun goes into the evaporation of water from the ocean, and part of this returns to the Earth as rain that can be trapped behind a dam. By virtue of its position, the water in a dam has energy that may be used to power a generating plant below, where it will be transformed to electric energy. The energy travels through wires to homes where it's used for lighting, heating, cooking, and to operate electric toothbrushes. How nice that energy is transferred from one form to another. There's your nice thought for the day. Suppose a car with a miracle engine is able to convert 100% of the energy released when gasoline burns, or 40 million joules per liter, to mechanical energy. If the air drag and overall frictional force on the car traveling at highway speed is 2,000 newtons, what is the upper limit in distance per liter the car could cover at highway speeds? In other words, what's the best gas mileage you can get? 40 million joules per liter. 40 million joules, that's the work that it can do, that's the energy, and work is equal to F times D. So I've got, and how much force are we applying? 2,000 newtons, that's the drag force. So in other words, what's 40 million divided by 2,000? What's the farthest you can go on a liter of gas? If it's 20 kilometers. Maximum 100% efficiency, 20 kilometers. Now that would assume that your car engine doesn't heat up at all, because some of the energy in burning the gas goes into heating your engine, right? So that would be usually gas efficiency is rated in liters per 100 kilometers. So if I went 20 kilometers in 1 liter, right, it's usually per 100 kilometers. So 100 kilometers would be 5 liters, right? What kind of gas efficiency do most cars get? Do you know? In liters per 100? Your car computer might tell you. Anyone know? Like, what's good in miles per gallon? 40 is really good. Yeah, if you're getting over 30, you're really, really good. Okay? 5 liters per 100 is maximum. I had a Chevy Venture that used to get about 8.6 liters per 100. Okay? Anything less than 10 is pretty darn good. Okay? But that's the limit, 5. Yeah, not 10 miles per gallon. That's my truck. Yeah. Yeah. Okay, so that's sort of the introductory to kinetic energy. Let's have a look at. Let's find out where that formula comes from, shall we?
Yay.
Thanks for patronizing. Work and kinetic energy. And you can choose to write these down if you want, or just the derivation, or just the sample problems, or whatever. I don't care. Choose whatever it is that you need to know to make it work for you. When work is done in an object, it may give it kinetic energy. It might give it potential energy. It can give it any sorts of energy. Quite often, it's kinetic, because you get it moving. Oh, sorry. Okay. Okay, so when work is done in an object, it could give it kinetic energy. In general, Work done is FD. We know that already, right? And that's equal to the energy that's transferred. If you do work, that energy is transferred and becomes the kinetic energy of the object. Could we call that delta EK? Sometimes they use KE instead of kinetic EK. I don't know what I prefer. They mean the same thing. EK, energy, kinetic, KE, kinetic energy. Either's good. Okay, but we need a formula, right? Oh, I think I was experimenting with. Yeah. I remember as a kid, my buddy, I grew up in a town where you didn't have to lock your car doors, and his favorite trick was to jump in your car and crank your radio and turn your wipers on and all that stuff. Those wacky kids. I don't know. Oh, I'm like, they leave their wipers on in case they have to. Okay. Okay, so anyways, W is FD. Do you remember that, of course, F equals MA? So I'm going to take this MA and I'm going to plug it in there and I'm going to get mad. Right? It happens.
I'll remember that one.
Do you remember this old chestnut? The Vx squared equals Vx squared plus 2AD? We used it yesterday, actually, right? We used the distance, and we used the final velocity 0, and we got the acceleration, and whatever, we figured out the initial velocity. So now, does this AD, will that work? Like, can I do something there? Well, if the object was at rest, what's the initial velocity? 0, so I can get rid of the VI squared. And would you agree then that AD is simply equal to V squared over 2? Now, what do you think I'm going to do? Maybe I'll pause there for a second. What am I going to do is that? It's kind of flickering there, isn't it? That new bulb better not be... Oh, you teenagers, so resistance to change. Surprisingly, teenagers as well quit. I think it's just generally people. This AD, I'm going to take V squared over 2 and I'm going to plug it in right there, right? Substitute this for the AD and W equals mad, and what do you get? Work done is kinetic energy gained, FD is MAD, or EK is equal to MV squared over 2. EK is equal to MV squared over 2. That's the formula.
The first, it wasn't the AD equals...
No, unfortunately, it's not the mad one.
What happened when it was like AD equals a VX squared over
Okay,
2?
okay, well, let me go back. Should I go back?
Yes, because I was...
Okay. So, W is FD, F equals MA, so MA goes in for F, and we get work done is mad, right? Okay, and then this one here, right? So I'm going to get Vf squared is equal to, if the Vi is 0, the initial velocity is 0, then I get Vf squared is 2AD. AD then is Vf, or just V over 2. And I'm going to take that, and I'm going to plug it in for AD right there. So work done is equal to mv squared over 2. And the work done is what? The change in kinetic energy. Right? If I started at rest, I had 0 kinetic energy at the start. So whatever work done becomes the actual kinetic energy. And you get EK is equal to mv squared over 2. Now, if you ever happen to be standing at Canada's Wonderland and you're needing to figure out how fast someone's going at the bottom of a big giant swing, that's the formula that you use in your head to figure that out. It does sort of sound like it, doesn't it? The rest of my family walked away from me at that point. Well, here's how it went, right? Because I knew the potential energy was mgh, and I estimated the height, and the potential energy has to become kinetic energy, and I estimated the mass, and I figured out pretty close what their velocity would be. Used my little nerd watch, had a calculator on it. No, I didn't have one of those, Zach, come on. EK is equal to mv squared over 2.
So what was the speed?
It was like about 70 or 80 kilometers an hour, I think. You're cooking.
You try and swing?
Did I try it? Oh, no, I'm not. I'm good at calculations. I'm bad at daredeviling. No, this was years ago, pre-concussion. If the object starts at rest, the work done is the total kinetic energy of the object. If the object starts at rest. What if the object doesn't start at rest? Well, then the work done is the change in kinetic energy. That's all. If the object starts at rest, the work done is the total kinetic energy, right? Like if it's at rest and I do 100 joules of work, how much kinetic energy does it have? 100. What if it's already moving and it has 100 joules of kinetic energy, and I do another 100? Now it's got 200, right? And the change is that extra 100. It'll make sense when you see some, oh, here it is here, kind of. If an object is already moving, the work done is the change in the kinetic energy. And the change in the kinetic energy is EKF minus EKI. Work done is the change in kinetic energy. Final energy minus initial energy.
So, hey, back it up.
Okay.
It's, it's
Okay.
yeah.
To there?
Yeah.
Okay. If it's already moving, the work done is the change in kinetic energy. All good back? Do you have the sample questions? They're on the one of the handouts, right? Okay, good. A force of 25 newtons acts for a distance of 16 meters upon a 2 kilogram object which was initially at rest. Assuming no friction, find its final velocity. Force 25. Distance 16. Mass 2. Initially at rest, excuse me. VI is 0. Find its final velocity. How am I going to do this?
And that equals to A, and then use the A and D, and the stuff like that, all that fun stuff, you know?
Yeah, equals the x squared.
Am I on the right track? Kinda?
I heard John say Vx squared equals Vx squared plus 2AD. But we don't have the acceleration.
Well, that's what I said, F equals MA.
F equals MA. To get the acceleration, we could. That might work. Could we go work is FD,
Oh, well, okay.
25 times 16. No? Yeah, there's probably multiple ways to do it. So this is the work transfer method kind of thing, right? So I do 400 joules of work. Where does that 400 joules of work go? Into kinetic energy, which is mv squared over 2. What's he saying about me?
You have no friends?
No, I'm over here on the south side. She told me she had to go.
Just take off, just let you know.
Yeah, that's it, I'm done. Tell me this kinetic energy nonsense. K equals mv squared over 2, so 400, my mass is 2v squared over 2. Well, that's convenient because what happens? 2 and the 2 cancel, and so v is simply square root 400, which of course is 20, right? Is that a nice, easy, simple way to do it?
Yeah.
I think so. So you can figure out from the work done how fast it's going. And basically, this is kind of what we were doing yesterday, right? We took the initial speed, and sort of work the other way. What's different about this one? There's a VI. Do you want to try it on your own? Or not yet? Okay. Force is 8. D is 5. Mass is 4. Already traveling at 4. Find the EKI, find the work done, find the final EK, and find the final velocity. Well, EKI, mv squared over 2, 4 times 4 squared all over 2, 16 times 4 divided by 2, I guess that's 16 times 2, that would be 32 joules. So it's already got 32 joules of energy. How did I just do that?
Now with the velocity,
Because there's an initial one already.
oh,
Yeah, the initial, yeah. EKI, initial kinetic energy, is this based on the initial velocity?
It's the regular guy.
How much work is done? $40. Where does that 40 joules go? Goes into giving it more kinetic energy. So what is the final EK? Well, work, change in kinetic energy, final minus initial, and as I take that to the other side, I get 72. And now, to find the final velocity, back to our new friend.
Oh, that was C.
This is C, yeah.
That was C, yeah.
Yeah.
Shoot.
Sorry.
No, it's okay. No, I put it in a weird spot.
Yeah.
But that's alright. It'll work still. Okay. Okay.
I think it's 6, am I right? Did I do that all right?
Well,
I think I did. I like it when I do it right.
that's good.
Yeah. So what is the overlying sort of concept here? The work done is the change in kinetic energy.
Hey, I got a bit lost there.
Where did the 4 go? I went 4 divided by 2 is 2. Right? So that's like 2v squared. And then I divided by 2, yeah. Is that okay? I guess if you want this to read 72 times 2 divided by 4, that would work, right? Is that what you want?
So bring back to the original one that you did because otherwise I lost
where's
it.
it go?
Is the V square? Oh,
This makes more sense.
wait.
It's like you know what you're doing.
I know.
Why did you move?
It's a curse, John.
Oh my gosh. Okay, what happened?
They didn't like this, so I took the 2 up there,
Okay.
and I multiplied by 2, 72 times 2, and then I divided by 4. And 2 divided by 4 is the same thing as divide by 2, which I had already before.
That was what you had.
That's what I had before. Yeah. Go ahead and try number 3. It's almost exactly the same. You've got a mass, you've got initial velocity. It experiences the force of friction. The only difference here is that instead of the force being positive 8, it's a force of friction of -2. And so what? It's actually negative work. It's going to take away speed.
Where the frick do you get a friction from this shit?
Is it exactly the same steps?
Yeah.
I think so.
Yeah, it's a car.
Get 400 joules?
Well, you guess you could just cross. Oh, I think so.
Minus 300 joules of work? Where does the energy go?
Away.
Into heat.
Did we eventually find out how much heat is produced?
300 joules. Warm stuff up.
How warm is the temperature?
How warm is 300? No, it depends on what your starting temperature is at, right?
So let's say we were making some popcorn.
Yeah.
How much do we pop for 300 joules of heat?
Probably not a lot.
So let's say maybe a handful of kernels.
How much you would have to measure it, Zach, by you would take, like if you took some food, that's what that oven's for, right? You take the food and you burn it,
Oh.
right? And you figure out how much heat it gives off. Basically, you figure out how much the temperature goes up, and then you can figure.
We should like put some popcorn in that baby.
Yeah, in that oven? I don't know if you can do that.
Let's test it out. We
Some
can
kind
feed it
of,
to people we don't want.
some kind of feed. Some kind of feed. That's what you think.
We're gonna eat. Ah! Oh,
It's not a microwave, it's an oven.
Calorimic oven, I think it's called.
Might be good.
The initial is 400, so when that minus 400 goes to the other side and becomes plus 400, you get, what'd you get for EKF? 100. Then back to here. Oh, over 2, right? Mass 2, V squared all over 2. What's your V? 10.
Don't make it easy like that.
Yeah, it'd be nice, eh? If the mass is 2, it makes it nice and easy. I could. Down or up? Right there. So the question is, how far do I have to push with 5 newtons to do that, make that happen? Let's see what we can find out. What do you think we should do?
Find acceleration, boy.
Really?
Yeah, and then I found work, and then I did that one.
I think that's the way to do it. Okay, give me 5 minutes of your time and then we're done.
I crushed it still.
Yeah?
Yeah.
Okay, so I think she's right. EKI MV squared over 2.
I'll put 4.
So that's going to be 4 times 10 squared over 2, which is 200, right? The final is also MV squared over 2. 4 times 15 squared all over 2. 15 squared, 225 times 2. 450, right? So, if I did have 200 joules of kinetic energy and I now have 450 joules of kinetic energy, my work done is the change in kinetic, which is going to be 450 minus 200. I did 250 joules of work. And how did I do that 250 joules of work? I did it by applying a force of 5 newtons through what distance? And what did you say, Hannah?
But I got it by doing something different.
Yeah, you will find that there's lots of ways to do these. But I'd like you to sort of focus in on the energy way of doing it if I could.
You can stop that.
Okay, so now what I want you to do is I want you to do those questions on that sheet as we finish up the period. You should have those done for homework.